So, hi everyone, my name's Arissa. I'm one of the Lanterna chemistry tutors. So, thanks so much for tuning in to our acids and bases series. We're currently looking at 18.2. So, this is going to be our second higher level video. And what we're going to be looking at mostly today is some of the calculations that you can get as part of the higher level syllabus. So we're going to start off with revisiting a familiar concept from our earlier videos. So if you remember, the ionic product of water, we derived from the dissociation reaction of water. So Kw equals to H plus times OH minus, which is a constant at room temperature. So 1 times 10 to power of -14. So this is also going to be available in your data booklet. And if you're asked a relevant question on paper 1, you'll definitely get this value as well. But it's always worth knowing kind of like where it comes from as well. So from that original reaction, we can also derive by taking the inverse log of all of these values that pKw equals to pH plus POH, which equals to 14. So that's kind of an important relationship to bear in mind. So let's have a chat then. So now that we know that this is the value for Kw at room temperature, what's going to happen to Kw when we increase the temperature? So when we go beyond 298 Kelvin, which is also 25 degrees Celsius. So in order to help us understand this, it might be useful to kind of derive the reaction that we started off with to kind of get the ionic product of water, and that's the dissociation reaction of water. So water dissociating into its ions, and then we got Kw by essentially writing out the equilibrium expression of the dissociation reaction above, and then we got rid of H2O because it's a constant. Come back to that. Okay, so let's have a look at this reaction then. So it's a dissociation reaction, so we're breaking bonds, and a little bit of like information from topic 5. Whenever we break bonds, that means we're putting in energy. It requires energy, and this means that this is an endothermic reaction. So this is going to be positive. Oopsies, let me write that properly. See, this is going to be positive delta H. So when we increase the temperature, we're going to favor the forward endothermic reaction. And what this means is that we're going to get more dissociation and therefore a greater concentration of hydrogen ions. So increasing the temperature, favoring the endothermic reaction, and that's going to leave us with more hydrogen ions. And when we have a higher hydrogen ion concentration, that also correlates with a more acidic solution, which means that we're going to have a lower pH. So we know that at temperatures of greater than 298 Kelvin, room temperature, our pH is going to go down. The solution is going to become increasingly acidic. Okay, my next question, however, is water still going to be neutral? And the answer to this is yes. So even though our pH has gone down, water is still going to be neutral because by definition, neutral means that we have an equal concentration of hydrogen to hydroxide ions. Let me just write that out. Perfect. So water is always going to remain neutral regardless, but at higher temperatures, we're going to have a reduction in our pH value. Okay, good. So, oopsies, yes, so that was your dissociation reaction of water over there. So let's move on to weak acids in that case. So if you remember from our SL videos, by definition, weak acids do not dissociate completely, so they do not fully convert into the ionic form. What this means, however, is that we cannot infer the concentration of the hydrogen ions from the concentration of the acid. So HA is how we sort of symbolize a weak acid in our calculation. So whenever you say HA, it usually implies that it's a weak acid. So the concentration of the weak acid is not going to equal to the concentration of the hydrogen ions. Okay, so what that means, therefore, is that to work out the hydrogen ion concentration and consequently the pH, we need to kind of take a different approach. We can't just input this into the formula straight away. So in order to work out this different approach, let's look at a dissociation reaction of a weak acid. So I've got a weak acid here dissociating into H plus or H3O plus and A minus. If I was to write the acid dissociation constant, which is Ka, so remember this is also very similar to the equilibrium expression. Let me just write that down, so equilibrium expression. So when we do an equilibrium expression, a bit of a throwback to topic 7, we always do products over reactants, right? So it's going to be H plus A minus at the top. So H plus and H3O plus are kind of interchangeable. And I'm going to have my reactants at the bottom. Good. I'm not going to include water because water is a constant, so we don't need to include that in this particular reaction over here. Good. So this is the formula, This is the formula for Ka. This is really important. So Ka, because it's a dissociation constant, essentially tells us about the strength of an acid. So if I have a large Ka, this means that there's lots of dissociation, and this means that I'm going to have a stronger acid, because we know that the stronger the acid, the more it dissociates. So that's why Ka is really significant. When you do your calculations, it's worth remembering that H plus and A minus exist in a 1-to-1 ratio, and therefore this can actually be simplified to Ka equals to H plus squared, because they are the same value, over HA. Okay, good. So that's definitely worth remembering, that H plus is squared at the top. All right, so what this also means is that we can derive pKa as well. So pKa we can derive from Ka, and that's just going to be negative log to the base 10 of Ka. So this is going to mirror earlier formulas on pH, which is going to be negative log to the base 10 of H plus. So that's kind of a formula that we saw earlier. So notice how they're really similar, right? In place of H, we're using Ka. Good. Okay, so this exact same logic applies for weak bases. So let's talk through that one. So we know that weak bases do not dissociate completely, and therefore the concentration of hydroxide ions is not going to be equal to the concentration of the base, because not all of the base dissociates into its ions. Therefore now, to work out the OH concentration and the POH concentration of the weak base, we need to use the approach that we used earlier for the weak acids as well. So this is going to be our dissociation reaction for a weak base. Notice also, by the way, it's probably worth mentioning, the equilibrium arrows are key here to show that there can be both a forward reaction and a backward reaction. Only in strong acids and bases do we use a direct arrow, because there's complete dissociation, so there's no backward reaction. So that's a quick note over there. Okay, so based on that dissociation reaction, we can actually work out Kb. So exactly as before, and this is really similar to the equilibrium expression. So we're going to do products over reactants. And again, I'm going to omit H2O because it's a product, because it's a constant. So I'm not going to include that over here. And exactly as what we saw earlier, Kb can also be simplified to OH minus squared over the concentration of the base. The reason we can do this as a square is because, remember, dissociation occurs in a 1-to-1 ratio, so the concentration of both of these is going to be equal. So they're the same unknown, and that's why we square it. And exactly as we saw before, the higher the KB, the stronger the base. Because we know that the stronger the base, the more it's going to dissociate, and therefore we're going to have a bigger value of KB. Perfect. And then last but not least, we can also derive PKB, which is also going to be minus log to the base 10 of KB. So this is going to mirror the POH scale because we're talking about bases. So it's going to be minus log to the base 10 of OH minus. Good. Okay. So it's worth mentioning that the higher the KB, the stronger the base. However, the lower the PKB, the stronger the base as well. Because remember, we're talking about an inverse logarithmic scale. So the smaller numbers on the scale are always going to be stronger. So for example, in a pH scale, it's always pH 1 and pH 2 that are the strongest. So it's really similar here. PKBs of 1 and PKBs of 2 are going to be stronger than larger PKB values. Okay, so a couple of relationships that I just want to talk you through as well. So it's worth bearing in mind that Ka, our acid dissociation constant, multiplied by Kb is going to equal to Kw. Notice how similar this is to our Kw reaction earlier. H plus times OH minus equals to Kw. So Ka corresponds to the H plus because it tells us about acids, and Kb corresponds to OH minus because it tells us about bases. Based on this reaction, the first reaction over here, we can derive that pKa plus pKb equals to pKw, which is 14 at room temperature. And this also looks very similar to our pH plus pOH equals to 14 relationship that we saw earlier. So it's worth bearing in mind how these values kind of like link together. So these two main relationships. The reason this is important is because it relates to conjugate pairs. So because Ka and Kb multiplied together give us a constant, this means that if I've got a higher value of Ka, so if my Ka is big, this means that my my Kb is going to be smaller because multiplied together, they're always going to give me the same value, which is Kw. So this means that a conjugate base will be weaker than the acid and vice versa. So the conjugate acid will be weaker than the base. So that's why these relationships are kind of crucial. All right, let's put this knowledge to the test then. So we're looking at a couple of past paper questions. So over here, you've got the Ka value, which is this one over here, and they're asking you what is the Kb for its conjugate base. So the relationship that we're going to use here is that Ka multiplied by Kb is going to equal to Kw, which also means that it's going to equal to 1 times 10 to the minus 14, so just 10 to the minus 14. I know that Ka is 10 to the minus 2, and therefore now I'm trying to find out what Kb is. So Kb is going to be 10 to the minus 14 divided by 10 to the minus 2. And when you divide them like this, essentially you can subtract the powers, so 14 minus 2, and that's going to give you 12. So what that means is that Kb is going to be 1 times 10 to the minus 12. All right, so that's going to be D as an answer. let's have a look at the next one. So now you've got the value of Ka, so that's what the acid dissociation constant is. So Ka is effectively 10 to the power of minus 5, and you're being asked the pH of a 0.1 aqueous solution of HA. So I know that HA is going to be 0.1, and in standard notation form, that's 10 to the minus 1. In a paper 1, it's always worth converting them to standard notation because it's easier for you to do the maths. It makes it quite hard without a calculator to work with decimal places. So in order to find the pH, I need to find the H plus concentration first. And in order to do that, I can write out the Ka relationship and see where I can input my values. So this was the formula for Ka that we derived in the earlier slide. So Ka is going to be 10 to the minus 5. And I don't know what H plus is, so H plus is still going to be an unknown, but I do know that HA is going to be 0.1, which is essentially 10 to the power of minus 1. So I got that up there. All right, so now let's try to solve for this. So simplifying this equation, I know that H plus squared means that I'm going to multiply these two together. So 10 to the minus 5 times 10 to the minus 1. When we multiply them, we can add together the powers. And so that's going to be 10 to the minus 6. Okay, so H plus squared is going to be 10 to the minus 6. Oopsies. So therefore, what I can do is I can essentially square root this. And when I square root this, the answer that I'm going to get is 10 to the minus 3. Okay, so 10 to the minus 3, and therefore the pH, remember, since H plus equals to 10 to the minus pH, oopsies, so 10 to the minus pH, this means that this value over here equals to our pH value over there. So the answer here is going to be B. All right, last but not least then, so this is a paper 2 question from quite a recent paper. So this is your 2018 paper 2, and we're looking at question 5. So you've been asked to find the pH of 0.01 moles per decimeters cubed of an acid solution, and you know the Ka. So whenever I see a question like this, I'm always going to start out by writing my formula for Ka. That's always a good place to begin when you're dealing with weak acids and weak bases calculations. Okay, so now I can input values. I know that Ka is 9.333 times 10 to the minus 6, and I know that Ha is going to be 0.01, and my unknown is going to be H plus squared. So if I put that into my calculator really quickly, so a quick note, when you are inputting this value over here into a calculator, I'd always recommend you to bracket it. It just means that your calculator is less likely to make any mistakes. So times 10 to the power of minus 6, and I'm going to multiply that by 0.01. Perfect. Okay, so what that's going to get me therefore is that H plus is going to equal to the square root of 9.333 times 10 to the power of negative 8. And if I square root that value really quickly, that's going to give me 3.055 times 10 to the minus 4. But we're not done just yet because we've been asked to find the pH. So now I'm going to input this into my pH formula, which is negative log to the base 10 of 3.055 times 10 to the minus 4. Perfect. And in order to get our answer, I'm going to turn us over to our mark scheme. So what you can see over here is that we've got the first part of the answer just by solving for H plus using Ka. So that's that first part of our question here. And the second part you get from inputting this value into the pH equation, which is negative log to the base 10 of hydrogen ion concentration. So your final answer is going to be 3.51, and the IB accepts some leeway there as well. Good. Okay, so thank you so much for joining us for this higher level video. I hope it's been really useful. Do stay tuned for our next higher level video, and also remember that on our website we've got lots of opportunities for you to get further support through online tuition and our revision courses as well. All right, cheers.